In this video we're going to look at circle theorem. The first part of the video is going to be a basic tutorial on the theorem. The second part we're going to work through some examples. Let's start off then. The arrow theorem. The arrow theorem states that the angles at the centre are double that at the circumference. So whenever I open this up, 105, 52.5 approximately. So when the angle at the centre changes, let's take this out to about 120, the angle at the circumference is half, so that's going to be 60. So that's the arrow theorem. The bow theorem states now that these angles at the bottom, the red ones, are equal. The angles at the top are equal. They're not necessarily, the green ones are not necessarily equal to the red ones, but these two top ones are equal and then the bottom ones are equal. And you can move these around to see that's the case. This app is on my website, which is linked just here if you want to check these out. They're interactive things that you can have a play with. What we've got here is a cyclic or cyclic quadrilateral. The opposite angles of the quadrilateral, when inscribed in a circle, are now adding up to give us 180. So 91 and 89 approximately, we can see that this is just about 90 each. If we change it, we can see 107 and approximately 73. So opposite angles of the cyclic quadrilateral equal 180 degrees. Angles in a semicircle have a 90-degree right angle. Wherever I put that now, if we've got a diameter and we've got a centre spot, this creates a 90-degree right angle. Okay, they're the first four we can look at. The next one now is going to be the tangent theorem. This states that if we have a radius and a tangent, it's going to create a 90-degree right angle. This is almost like putting a barrel out and then putting a plank on a barrel. It's just going to sit on the top and create a 90-degree right angle. We have the alternate segment theorem. The alternate segment theorem is the one that often causes a few problems. All we've got to think about now is the angle opening up to the right is the same size as the angle opening up to the right. If we see this changing, we can see quite clearly when this changes, they are equal. In the same way, this angle opening up to the left is going to be the same as this one right here. The chord centre theorem, we don't really need to look at this, but essentially if you bisect two chords, where the two bisectors will meet in the middle and create a centre point. And then finally, one we do want to know is the dual tangent theorem. When I say this is dual tangent theorem, as with all the others, they may have different names. What we can see from this now is the distance from the circumference to this point, anywhere we go, is going to be equal. And this creates two congruent right angle triangles. So we've got a right angle here, we've got a right angle here, and these points are equidistant from the point here to here. Okay, so that's the dual tangent, and we can see wherever we go with that, it's the same distance from here to here as it is from here to here. So let's work through some of these and we'll see where we go. It's important to appreciate I've not looked at any of these, so I'm going to be doing them as I go. If I do them differently to the way you do, drop me a note if you think there's a quicker way. There probably is a quicker way, as I'm going to do them whilst I'm talking. Also, if I have to revert to my calculator later, I apologise, as I'm going to try and get through quite a few. Okay, let's start off then. This one right here, we've got a diameter, we've got the O, the centre here, we've got 25B and A. We know that angles in a semicircle are 90 degrees, or they have a 90-degree right angle. So there's our 90-degree right angle. So 90 plus 25 gives me 115. We need this to equal up to 180 as it's in a triangle. So this must be now 65 degrees. 90 plus 25 is 115. 65 added is going to give us 180. Okay, another similar one. So we've got now a diameter, 18 degrees. We know the angles at the centre, at the circumference, if we're in a semicircle of 90 degrees. That gives me 108, so this one will be 72 degrees. Okay, this one here, we've got the two of them this time, so we can see now that this diameter here will give us now a 90-degree right angle at the circumference. 90 plus 16 is going to give me 106, so this will now be 74. We could just say opposite angles in a quadrilateral are going to be equal, so we know this is 90, but we also know it's 90 because it's a right angle in this triangle here. 90 plus 14 is going to give me 104, so this one right here is 76. And if we add these ones up right now, we can see that those are going to give us 180 also. Okay, let's look at this one. Straight away, this is going to be 90. We know this one's going to be 90 for two reasons. A, these are two opposite angles, these must be equal to 180, and also we've got two triangles in a semicircle. Okay, so if this one is going to be 90, adding this gives me 148, so this one now must be 32 degrees. You might just want to say, I know this is 90, so these two need to add up to 90. This one right here, what we're going to have, if that's 32, this one must be 58. And as stated, lots of different ways of looking at that one. This one right here, slightly different, but it does introduce something slightly more interesting. If we consider now, this is a radius in a circle, and this is a radius. This creates us now an isosceles triangle here. So this one must be 60. The base angles of an isosceles triangle are equal. 60 and 60 is 120, so this one must be 60 as well. So we've actually got an equilateral triangle, okay, which is quite interesting. If this is 60, we've now got the angles in a semicircle, so this one is going to be 30. We've got another now, an isosceles triangle, so this is going to be 30. That gives me a total of 60. This must be 120, and we know that anyway as we've got an angle on a straight line. Okay, opposite angles of a cyclic quadrilateral equal 90, or we can just say angles in a semicircle equal 90. This is going to be 90. Adding these two gives us 131. So this one right here is going to have to be, what's that going to give us? 49 degrees. Okay, so 49 and 41 give us a total of 90. 90 and 90 are 180. Okay, so as you can see, lots of different approaches on that one. This one here, we've got now the 40 degrees, angles in a semicircle, this must be 50. That right there and that right there are radii, so this one is going to be 50. We've got our little isosceles triangle, therefore 50 and 50, this is going to be now 80. Angles on a straight line, 100, 180, and this is 40. As we know that too is an isosceles triangle, or we could have worked it out that way. So again, lots of different approaches. This one here, we can look at this in the way and state that E is going to now be 100, we need 180 with these two, so this is going to be 88. So we've got 88 here. We could say now that this angle right here is going to be the same as this one. So this one must be 44, and this one must be 44. We can say that these two have got to be equal to 92, so these ones are going to be 46 and 46. We can use the bow theorem right here to just say that A and F are also equal. So this one too is going to be 44 degrees. And with this one, there are absolute million one ways you can do it. I'm sure if I was sitting down with these in front of me, I'd go a different route. But as I'm doing them while I'm talking, hopefully they should make some sense. Okay, this one here, what we can do is the following. We've got now the isosceles triangle. So this one is going to be 20 degrees. 20 and 20 is 40. This must be equal to 140. Okay, we now can see we've got a bow. So this one must be equal to 20. This one must be equal to 20 also, as we've got a bow and an isosceles. If we consider now, we've got angles in a semicircle, so this one must be 70 degrees, as it's going to have to equal 90. If that's 70, this one's 70 for a whole host of reasons, angles in a semicircle or isosceles triangle. So this is going to be 40. We knew it's 40 anyway, as it was on a straight line. So take your pick which way round you go on that one, and there's lots of different approaches. Okay. We know a tangent creates a 90-degree right angle. So here we go, tangent, we've got radius. So 90 plus the 25 is 115. So this one must be 65 degrees to make up for 180. Okay, next one. We've got, again, the dual tangent. So this is 90, this is 90. Leaving us now, these two must be equal up to 180. So we're going to have 74 degrees. This one here, what have we got? Opposite angles. So that's 10. We can state that this is going to be 90. This is going to be 90. So all we need to do is make these two add up to 180. So that's 170. Okay, what we've got here is the following. We know that the opposite angles in a quadrilateral will be equal to 180. So this must be 110, as that's now equal 180. This one must be 140 degrees. And if we look at that, if we add them all up, they're going to be equal to 360 degrees. This one here, what we can automatically do with this one is place on here, let's put that on, that's going to be 130 degrees, angles on a straight line. These two right here, these need to equal up to 130, so this is going to be 65. This one too will be 65. Opposite angles in the quadrilateral must be equal to 180, so this is going to be 115. And now if we look at this one right here, what we can either say is that all of these can equal up to 360, or the opposite angles can equal up to now 180. If I add those two, I'm going to end up with 120, so this one must be 60. And of course, if we add these up, that's 190. If I add those two up, it's going to be 170. 170 and 190 makes 360. Okay, we know that this is going to be a right angle triangle, so we want the length of the diameter. What we've got is a little Pythagorean triple. So this is 3, this is 4, 3 squared plus 4 squared square rooted gives us 5. So the diameter across here, the distance across from this point to this point is going to be 5 units. This one here, we've got a tangent. So a tangent creates a right angle. Again, we've got a right angle triangle and another Pythagorean triple. This is going to be 8, this is going to be 10. 10 squared minus 8 squared square rooted will give us 6. So it's an 8, 6, 10 Pythagorean triple. Okay, angles at the centre are double that of the circumference. This is an example of the arrow theorem. So if that's 73, this is 146. So nice and straightforward. This one here, angles at the centre are double that of the circumference. So this must be 35. All we've got is an arrow here. We could look at this as another arrow, or we could simply look at it as a bow. So if C is 35, D must be equal to 35 also. This one here, we can now look. We know that this is going to be a 90-degree right angle. Angles in a semicircle are 90 degrees. 90 plus 47 gives me 137. So all I need to do is make these two add up to 90. So that's going to give me 43 degrees. So 43 and 47 are 90. Now what we've got here is a bow with this one. So this must be now 43 degrees. So there we go. X and Y have been found. And different approaches as usual. Okay, next one here. Let's look at what we've got here. We can see from this that this is going to create an isosceles triangle. So if this is going to be 50, we can say now that this one right here and this one here have got to be equal to 130. That means D is 65. Now consider the following. If D is 65, A is 65, as these are a bow. So this one's 65. Angles in a semicircle equal 90, so this one is going to have to be equal to 25. What we've got now is C is going to be equal to B. What we've got is the following. If we consider now that this is 25, C is also going to be 25. If you want to look at this another way, this right here is a right angle. This one is going to give us the 25. So this is 25, that's 65, that's 90, and you could look at it as a bow, or you could look at it as an isosceles triangle. So C is 25 also. And with that one, just looking at it now, I'm thinking of another way of doing it. It's entirely up to you really. You pick it to bits, but they're the values we should get. Okay, this one right here, we've got now an isosceles triangle. So if this base angle is 27, this is 27. That gives me 54, so this gives me 126 degrees. We've got a little triangle, angles at the centre, double that of the circumference, so this is 63 degrees. So creating a little isosceles triangle, take the top value, half it, and that is C. Right, what else have we got? Okay, this one's quite nice. Angles at the centre are double that of the circumference, so that's going to be 55 degrees. Opposite angles of a cyclic quadrilateral have to be equal to 180, so this is going to be 100 and what's that, 125 degrees, and that will give me my 180. So I say if that's 110, that's 55, opposite angles equal 180. And with that one, yet again, a few different approaches. This one right here, these are the ones that cause people hassle. Let's just consider this angle right here. This angle is going to be 280 degrees. Okay? Angles at the centre are double that at the circumference, so this one right here is going to be 140 degrees. All we've done now is brought the legs up of the arrow. So if we pull those legs down, we've actually got the arrow theorem. So angles at the centre double that at the circumference, so C is going to be 140. Okay, let's see what else we've got. This one here, we could look at this in a few different ways. We know that this is going to be now 90 degrees. So that one's going to be 90. That gives us a 132. So this one is going to have to be now 48 degrees. So we've got 48 degrees in total, and all we need to do now is find B. This is a quadrilateral right here, so this must be 75 degrees. These are opposite angles right here in the quadrilateral. We can see the quadrilateral is touching here, 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 and here. So I've done this a couple of different ways. It's entirely up to you, but that's where we should wind up. 42 and 48 and 90, 90 there, right angle in the semicircle. Okay, this one right here. A few different approaches again. We could look at this now. We could take this to be the angle on the straight line, and that is going to give me 75. Therefore, this is going to be 105. So opposite angle right here, we could look at that one now. Opposite angle, this must be 75. This one right here, opposite angles, this must be 80. Therefore, on this one, we can have now 100. And you can use the alternate segment approach on that if you wish. Looking at it, yeah, you should be able to. But essentially, if we look at it now as the opposite angles of cyclic quadrilateral and angles on a straight line, it works out fairly nicely. Okay, let's look at this one right here. Now with this one, what we can do is look at the opposite angles. We've got now a quadrilateral here. Opposite angles of a quadrilateral must equal up to 180. So this one right here is going to be 65 degrees. If we consider this one right now, this is 115. 115 plus 65 is 180. Now let's take the big triangle here now. So what I've got is the following. This big triangle is going to give me now 65 and 85, which is going to give me 150. So that is going to be 30 degrees. This one right here, angles on a straight line, this has to equal 180, so this has to be 65 degrees. Therefore, this one right here, we've got 95 in total. That's going to be now 85 degrees. And looking at that one, there are some alternatives that you could take. So there we go. So I've looked at a big triangle and then looked at smaller ones. Just thinking of some additional ways to do that one. So that's done. Okay, let's have a look at another one. Okay, this one right here. What we've got is the following. This is going to be on a straight line 100. Therefore, this opposite angle right here in the quadrilateral is going to be 80. Angles at the centre are double that of the circumference. We have the arrow, so this must be 160 degrees. So all I've done, straight line there, 100 degrees. Opposite angles need to equal a 180 in the quadrilateral. Then angles at the centre are double that of the circumference. And as I keep stating, loads of different approaches. Don't think that this is the only way or the best way. You have a play about with them and see where you go. Okay, let's look at this one here. Now with this one, we can fill in a fair bit of information. I'm going to take it and take some bits from it. Automatically, I can spot now. In fact, do we need that one? We can do it anyway. So this one and this one right here are going to be 65 each. That's the bow. If we look here, we've got a bow, and the bow is going to be with here. Let's grab this one up. So this one here, angles at the centre are going to be double that of the circumference. So let's grab 15. This has got to be now 30 degrees. Angles at the centre, imagine this was up here. That would give us an arrow. So we've got that one sorted. So that's going to be 30. In fact, let's just tidy that up. and let's see what we can do on this. So that's going to be now 30 degrees. Let's put that in. So that one there is going to be 30. We've got an isosceles triangle, so this one right here has got to be equal now. These two must be equal to 150, so this is going to be 75 degrees. So we've got this one being equal to 75 degrees. If we consider now that this is going to be a right angle, what we can do is find the value of this one. That's 90 degrees, so therefore this one is going to be 75 also. Okay, now if we look at these two right here, what we've got is the opposite angles of a cyclic quadrilateral up here. So our quadrilateral, so these are going to be now, adding these two together, we're going to have 150. Although it doesn't look like it now, this angle here is going to give us the 150. The opposite angle to that is this one right here, which is going to be, despite it not looking that way, 30 degrees. Now, if we consider this one here, we've got now a 90 degree right angle here, so this one is going to be 60 degrees. That's poorly drawn, but hopefully that makes some sense. Okay, let's continue now. Let's move on. Right, this one here. Let's see what we've got. We know that this is going to be a 90 degree right angle right here, okay? So if we take this, that's going to be a 90 degree right angle with the tangent. If we first think what we've got now, and I'm going to look at this like so, I'm going to take this to be a triangle. So what we've got here is the following. This one is 90 and this one is 25, that's 115. That must mean that this one right here has got to be 65 degrees to make up the triangle. We know that angles at the centre are double that at the circumference, so this one is going to be 32.5 degrees. So all I've done is added these two to get 115. This is 32.5, and now these must be equal up to 180 degrees. So what's that? 147.5? 147.5 degrees. Opposite angles in the quadrilateral are going to be equal to 180. That's quite, and again, I'm open to suggestions on different approaches to that. I've looked at the tangent, that's 90 degrees, worked out that's 65, then opposite the angles at the centre double that of the circumference, so that must be 32.5, therefore these two must be equal to 180, and as stated, if there's a quicker way, please do write a comment. Okay, let's look at this one right here. So this time we don't have a centre spot. We know that this right here is going to be x as well. We've got an isosceles triangle. Opposite angles have got to be equal to 180, so this must be equal to 112. Okay, so these two must be equal up to 68 in total. So this one's going to be 34, and this one's going to be 34 also. So all we've done, opposite angles, that gives us now that this must be equal to 112, and then these two must be equal to 34 each, as they need to equal up to 68. Okay, let's have a go at another one. Opposite angles are equal to 180, so what we can say then is these two are equal to 180, so 3x plus 30, I've just added the x's together, is equal to 180. Subtracting 30 from both sides, 3x is equal to 150, and we can see that x is going to be equal to 50 degrees. So on this one, that's 50 degrees, and then on this one, it's got to be equal to 130 degrees. Opposite angles of the quadrilateral are equal. Okay, let's have a look at another one. Okay, these two are equal. We know this is a bow theorem, so we can say 2x minus 10 is equal to x plus 30. So subtracting x from both sides and adding a 10, x is going to be equal to 30 plus 10, which is 40. So this one, we can see that's going to be 70 degrees, and quite clearly, if x is 40, that's going to be 70 degrees, as we know those two are equal. Okay, let's look at this one. Let's think what we can do. Different approaches. This is an alternate segment theorem if we want it. We've also got now that this is going to be a 90 degree right angle in total, as we've got now the radius and a tangent. So if this is going to be a 90 degree, what we can say is this is going to be 55. That gives me the 90 degrees. So this one too is going to be, by the alternate segment theorem, this is going to be, well in fact let's look at it an easier way, let's go with that way, at 90 degrees. Semicircle, so that's now going to give us a 35 degrees, and that makes sense. Those two plus that one are 180. Or we could have just looked at it now and stated that the alternate segment is going to be the same as that one. This is going to be 90, so quite clearly now what we're going to have here, the 90 plus the 125, this one is going to be 55 degrees. And there are lots of different properties that you could have used for that. So if we now look at the big triangle, we've got 110 plus 70 is 180. So different approaches there. Okay, let's look at this one right now. What we've got on here is a centre spot. We've got this point A, and then we've got the 117. This A and the 52 have to be equal to the 180 when added there. So if I add that, that's giving me 169. So this must be 11 degrees. So adding these two is 169. This is 11 degrees, as the opposite angles of a quadrilateral must be equal now to 180. We've got a tangent here, so these two have got to be equal now on here to 90 degrees. So this one is going to be 79 degrees. B is going to be 79 degrees. Now consider that that's all 90 degrees. We can get this one by doing the alternate segment. This is an alternate segment. B and C are alternate segments, so that's going to be 79. And now if we look at this one too is going to be 79. As we know, the points from here to here are equidistant. So what we've got in total now, let's check that one. In fact, let's get this right. That's 11 degrees. That's going to be 79. So 90, 90, and this one right here. So let's work this out. So let's get my head around it. What's D going to be? 22. D is going to be 22. Let's just get that there, 22. Because that's now another triangle. I'm kind of having a bit of a think on that one. That's perfectly fine. So those two are going to be equal to 158 in total. 22 makes it that triangle. So that's perfectly fine. That's done. Cool. Sorted. Okay, let's look at this one. Now this one, if we think about it now, we can go two different ways. I would like to just spin this round and turn it looking something like that. If we look at it like that, we can see that we've got an alternate segment. The alternate segment is A and the 52. So this one right here is an alternate segment with that one. So if we turn it back round, what we can do now is state that this, let's put that on, A is going to be 52 degrees, let's put that there, alternate segment, and then angles at the centre are double that of the circumference. So this is going to be 104 degrees. 104, not 1040, 104 degrees. I think that's meant to be a degree sign. So there we go, angles at the centre double that of the circumference, and we got the alternate segment theorem. Okay, there we go. As you can see, by the end of it, I'm running out of steam. We've looked at a few different types. These last couple, slightly harder with the alternate segment theorem, but hopefully that's given you a good insight. And as stated, I've been doing those as I go, so if there are any things that could be done better, please do drop me a line.